Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking a lot about ENSO and PDO. ENSO stands for El Niño-Southern Oscillation events. PDO stands for the Pacific Decadal Oscillation. We'll learn a little bit more about what those are here in the next 30 or so slides, but let's go ahead and jump on into it. So let's start off with some definitions. So first off, we have an anomaly. A without nomos equals law. So without law. These are basically maps that show the difference from normal conditions. So we have our averages. Anomalous conditions are those that go outside of average. Sea surface temperatures, or SST, anomaly maps are useful for identifying unusually warm or cool waters. Positive sea surface temperature anomaly values equal water warmer than normal, and vice versa. Negative equals water cooler than normal. El Niño-Southern Oscillation, or ENSO, derives itself from the Spanish word for the child. El Niño is actually reference to the child, capital C, in reference to baby Jesus. So basically equals warm surface currents in equatorial eastern Pacific waters that occur periodically around Christmas time, hence the name. Southern oscillation means a change in atmospheric pressure over the Pacific that accompanies an El Niño event. ENSO describes a combined oceanic and atmospheric disturbance cycle. So let's go ahead and talk about what the ENSO cycle is. Well, first off, it's a naturally occurring phenomena. You have these equatorial Pacific fluctuating between warmer than average El Nino and colder than average La Nina conditions. It basically ebbs and it flows. The changes in sea surface temperatures affect the distribution of tropical rainfall and atmospheric circulation features, or southern oscillation. Changes in the intensity and position of jet streams and storm activity occur at higher latitudes. So these have far and wide-reaching effects. So if we're going to look at and start diving into kind of a brief history of El Niño-Southern Oscillation, we can see that it's been documented as far back as the 1500s as a phenomena along the coasts of northern Peru and Ecuador. So it was a term used to describe annual appearance of these warmer waters around Christmas time. In some years, the warm waters appeared earlier and lasted longer. Eventually, the term was applied to the periods of anomalous warming. Stronger events disrupted local and fish bird populations, which obviously had some far-reaching effects for the people living in those areas. And in modern times, or at least maybe the 90s, we had Chris Farley's famous skit from Saturday Night Live, I am El Nino, which is Spanish for the Nino. If we look at the history of the Southern Oscillation, beginning in the 1800s or so, scientists began to describe large-scale pressure fluctuations. A gentleman by the name of Sir Gilbert Walker and colleagues extended the early studies and determined that a global-scale pressure fluctuation, or the Southern Oscillation, is related to rainfall anomalies in many areas of the tropics. For example, India and South America. The Southern Oscillation was used as a basis for seasonal rainfall predictions circa 1930. The discovery, if we kind of keep diving into this, El Nino and the Southern Oscillation were studied as separate phenomena until the 1950s to 1960s. Important works by Berlage in 1956 and Bjerknes in the late 1960s demonstrated a link between these two phenomena. Studies at the time also showed that anomalous warming of the waters during El Nino extended over a large portion of the equatorial Pacific. So looking at these as a coupled ocean atmospheric system is crucial to understanding how they impact weather across our world. And some pretty wild things can happen when the El Nino is in its full swing. Same thing for the La Nina, but we'll dive into those here in just a bit. So if we look at the ENSO events, the atmosphere drives the ocean and the ocean drives the atmosphere. We've talked about this in the last number of videos. It gives us a positive feedback between the ocean and atmosphere. Example, Weaker equatorial trade winds lead to colder water upwelling in the east. That'll decrease, leading to surface warming of the ocean, which leads to reduced east-to-west temperature gradients, which can lead to weaker equatorial trade winds, etc. You can get the idea. It's a positive feedback loop. It's a connected system. What happens in one impacts the other. So if we look at what is average, we look here, we've got normal conditions, and you can see that in that bottom right there. So we've got, if we look at off the coast of New Guinea, for example, we've got this warmer water pooling, we've got hot air rising, condensing, we've got this Walker circulation leading to our trade winds at the surface. In the oceans, we've got this warmer air. It's warm air being heated by the sun. We've got this thermocline. So as water is descending, it's kind of cooling a little bit. This thermocline is our colder area. We've got upwelling along the coast of South America. So cool, lower water. Winds and sea surface temperatures are coupled. The sea surface temperatures influence the winds and vice versa. During normal conditions or average conditions, easterly trade winds help push warm water to the western Pacific and upwell cold water along the equator in the eastern Pacific Ocean. Warm water heats the atmosphere, the air rises, and low-level trade winds converge towards the warmer water. Subsiding air occurs in the eastern Pacific Basin. We can see in that image on the bottom right there, that kind of nicer looking graphic, get a good kind of three-dimensional sense of where, one, things like winds are blowing, where the Walker circulation cell is cycling, where our warm ocean currents are found, where that upwelling occurs along the coast of South America, and we get this general sense for this circle, this circulation pattern between the atmosphere and the oceans, kind of helping propel one another forward. Now, during El Nino conditions, if we look off the coast of New Guinea, you've got this warm pool sloshes towards the east. The easterly trade winds weaken. And a thermocline deepens and the cold water upwelling decreases in the eastern Pacific. We see that over here, right? So this cold water upwelling decreases. This cold water isn't getting as high up as it was previously. So note the location of the warmest sea surface temperatures, somewhere greater than 28 degrees Celsius, determines where tropical convection will be located. Convection shifts eastward over the central and or eastern Pacific Ocean. Convection becomes suppressed over the far western Pacific Indonesia area. If we were to look at this, we have basically the generation of a weak Aleutian high as far as our circulation patterns go. We have warmer air or warmer conditions that exist over much of the northern United States throughout Canada. We've got this extended Pacific jet stream and amplified storm track. So we have bigger storms that can come in and strike the Baja Peninsula, the Gulf of California, kind of the southern US into Mexico and Texas. This bringing with it from the Pacific this wetter air. We move across, kind of bringing it back through the Gulf and inundating Florida and whatnot. We've also got this drier air that hangs out over the Midwest, Illinois, Missouri, down into Arkansas and kind of the South. So we've got kind of this entire change of average patterns here in North America because of an El Nino event. We've got this kind of low pressure system that hangs out over here, a very weak Aleutian high. So the effects of severe El Nino can be pretty widespread. We've got things like marine life are impacted, floods can be strengthened, coastal erosion is worse, especially along these coasts here. Drought can happen throughout much of the regions. We see that evident here. Coral reef damage, bird life can be impacted because they're having impacts to their food source. Forest fires and tropical storms. And it's also been linked to some tornado severity increases as well. Impacts are generally more extensive during the northern winter rather than the southern winter. So if we look at warm episode relationships from December to February, we see warmer air, wetter and cooler air in the south of the United States over here, drier air through much of Oceania. We see that here. Kind of limited effects for the most part in South America and off the coast of Madagascar and in Africa. But a general warming also we see in the northern hemisphere again, in India, China, Japan areas. Typical global El Nino impacts in Indonesia. For the life of the event, we typically see drier conditions, as we see in northeast Brazil and Central America and Mexico during kind of spring through fall. Along the west coast of South America, we typically see wetter conditions in March through May. In Central South America, we typically see wetter conditions in June through December. And then in Southeast Africa, we typically see drier conditions in December through February. We look at anomalous precipitation in millimeters per day. There are strong El Nino episodes. Look at the El Nino that we see in January to March of 1983, and again in January to March of 1988. Some pretty large anomalous precipitation evidence occurring here and here. Rainfall departures as large as plus or minus 8 millimeters per day, 30 inches in a season, result in changes in the patterns of tropical heating and changes in the position and intensities of mid-latitude jet streams and planetary waves. During moderate El Nino episodes, rainfall departures are less. During weak to moderate episodes, smaller changes can occur in the patterns of tropical heating and in mid-latitude jet streams and planetary waves. Again, in, for example, 87 and 92, say moderate episodes, we don't see that anomalous precipitation extended nearly as far as we did in the previous slide. And then sometimes we have La Niña events. So this is the other side of the coin, if you will. So here we've got more enhanced convection occurring. We've got stronger upwelling occurring. This upwelling becomes more shallow. So if we look at our little graph, a few things are happening here. We've got a strengthening of our easterly trade winds. The thermocline becomes more shallow. You can see that here. It's much more shallow with upwelling colder water along the coast of South America and increasing in the eastern Pacific. And convection becomes stronger over the far western Pacific Ocean in Indonesia and more suppressed in the central Pacific. So got this big high pressure system that sets up here and a low pressure system that sets up kind of getting towards Australia off the coast of Papua New Guinea. You see here. So you've got this warm pool. Again, that thermocline becomes much more shallow with stronger upwelling, stronger trade winds, and more convection. And you can get more rainfall in some of these instances. So if we look at a La Nina during a strong Aleutian high, or we get a strong Aleutian high here, our jet stream can be a lot more variable. So during the winter, this winter polar jet stream can dip and meander much further to the south, bringing this massive movement of cold air down towards us. It can be wetter in the Pacific Northwest, drier along the Four Corners region throughout much of the south, along with warmer along kind of the south into Texas and kind of back around. And it can be wetter in our neck of the woods, Minnesota, Wisconsin, Illinois, Indiana, Ohio. Mid-latitude impacts are generally seen during the winter season, during global La Nina events. So during December through February, you can see it's much wetter in Oceania region, drier and cooler in that stretch between the western coast of South America, extending kind of towards the dateline areas, about 180 degrees. Drier and warmer in the south of the United States, a bit wetter south of the Great Lakes into the Pacific Northwest. Cooler along the coast of Alaska and British Columbia into the interior of Canada. Cooler around Japan. Cooler around the west edge of Africa. We see these effects kind of spanning out here. During June through August, we see the majority of the impacts focused in kind of Southeast Asia and into Australia, Oceania region. Typical global La Nina impacts include in Indonesia during the life of the event, wetter conditions. Northeast Brazil during March and May, wetter. Central America and Mexico from May to October, wetter conditions. The West Coast and South America, March through May, drier conditions. Central South America, June through December, drier conditions. And then Southeast Africa, December to February, wetter conditions. From anomalous precipitation in millimeters per day, rainfall departures as large as plus or minus 8 millimeters per day, 30-inch season result in changes again. Here we can see a striking difference. So much drier where we had those major anomalous pulses upwards of 8 millimeters of rain per day extra in that kind of central Pacific region. But we see kind of along the coast of New Guinea, off the coast of, well east of the coast of Africa, and then again in kind of Oceania region, Southeast Asia. We see that happening pretty prevalent with marked dry regions and marked wet regions. So if we look at the El Nino recurrence interval, kind of looks like this. Every couple of years or so, we swing from El Nino to La Nina. The typical recurrence interval for El Ninos is every 2 to 12 years or so. The Pacific has alternated between El Nino and La Nina events since the 1950s. We are currently leaving a La Nina and gearing up for an El Nino, at least as of recording this video, in March of 2023. So we are gearing up for an expected El Nino event to start. So if we were to compare El Nino and La Nina phases, we see signals in tropical Pacific. That's where the majority of it's coming from. Sea surface temperatures are different, precipitation is different, sea level pressure is different, southern oscillation in high and low phases is different, and then low level winds and thermocline depth differ as well. We saw those in all three of those nice little graphics when we went from average to El Nino to La Nina. Here we can see sea surface temperatures again. Just notice those broad differences from El Nino events to La Nina events. We can see that in 1998 and 1989. The equatorial cold tongue, as you could call it, is weaker than average or absent during El Nino, and that's kind of in reference to this feature right here, resulting in positive sea surface temperature anomalies. The equatorial cold tongue is stronger than average during La Nina events, resulting in negative sea surface temperature anomalies. During precipitation, we've got enhanced rainfall over warmer than average waters during the El Nino, and reduced rainfall occurs over colder than average waters during the La Nina. For sea level pressure, during the El Nino, positive sea level pressure anomalies over the western tropical Pacific, Indonesia, and Australia are observed. Negative sea level pressure anomalies over the eastern tropical Pacific, middle and high latitudes of the North Pacific, and over the United States are observed. And the opposite pattern exists for the La Nina. The pressure seesaw between the eastern and western tropical oceans is known as the Southern Oscillation. As far as low-level winds and thermocline depth, During La Nina, we've got stronger than average easterlies that lead to a deeper, shallower than average thermocline in the western equatorial Pacific, the west coast of South America, but the eastern Pacific. During the El Nino, weaker than average easterlies lead to a deeper, shallower than average thermocline in the, again, western equatorial Pacific. So the eastern Pacific, but kind of the west coast of South America. And here we can see the differences in the jet stream. So notice that during La Nina phases, we've got substantial meandering and variability within that polar jet and variability within the Pacific jet, which can lead to drier conditions overall in the south because all that moisture is being dragged northward where it would originally be kind of moving across here as it does during El Nino phases. So we have an extended Pacific jet stream and amplified storm track drenching this region along the southern coast of the United States through Mexico, the Baja Peninsula. And then our polar jet stream is a little bit more contained to the north, so we might not see as much intense cold air dipping down towards where we live here in Wisconsin and Minnesota. And then finally, I'm going to knock it off with the Pacific Decadal Oscillation, or PDO. During warm phases, you can see on the left here, cold phases, you can see on the right. So the Pacific Decadal Oscillation is a long-term ocean fluctuation within the Pacific. It's often described as a long-lived El Nino-like pattern of Pacific climate variability, waxing and waning every 20 to 30 years or so. From ocean surface topography data together with other ocean and atmospheric data, scientists can determine whether we're in a cool phase or a warm phase. The cool phase is characterized by a cool wedge of lower than normal sea surface heights and ocean temperatures in the eastern equatorial Pacific, and a warm horseshoe pattern of higher than normal sea surface heights connecting the northwest and southern Pacific. In the warm or positive phase, the West Pacific Ocean becomes cool and the wedge in the east warms. So what does that do? Well, more frequent and stronger El Nino events occur during periods dominated by a warm phase, a warm PDO. More frequent and stronger La Nina events occur during periods dominated by a cooler phase. In 2014, we think we flipped from a cool to a warm phase. So potentially more intense El Nino events than we would typically have. So the change in the location of cold and warm water masses alters the path of the jet stream. Put simply, the jet stream in the northern hemisphere delivers storms across the United States. The PDO phase that we appear to have entered will act to steer the jet stream further north over the western United States. So we can kind of see a couple different things here. We see cool phase from roughly 1890 to 1924, a cool phase from 1947 to 1976, and a cool phase from 1998 to 2013. Likewise, we see warm phases on those interim points from 1925 to 1946, and in 1977 to 1988. And apparently, we've flipped over here. Sometime around 2014, we maybe flipped back to a warmer phase. We'll see how prevalent that is, but it could mean to more intense El Niños, which can lead to much greater weather variability during those events. Lost my cursor here. There we go. So brief recap, we talked about the El Niño-Southern Oscillation and Pacific Decadal Oscillation and how those really impact weather events across our world. So I hope you enjoyed that video, and we will see you in the next one. Thanks.